Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the components of F that act along the road AC and perpendicular to it. Point B is located at midspan of the road. The problem is coming from the engineering mechanics textbook 13th edition by R.C. Hibbeler. All right. So we have the rod, okay, that is connected at A and C, and there is a force that is applied at the midpoint of the rod AC, okay, and the force is exerted from B to D. So we have been asked to determine the components of F that act along the road AC and perpendicular to it. So this is what we want to find. We want to find a component of the force that act along AC like so. We want to find this force. Okay. So imagine this is the center of where F is applied on the rod. So we want to find this component that I'm going to call F parallel to AC. Okay, and not only that, they've also asked us to find another force that's perpendicular to AC. So I'll draw it from the same point like so. Okay, this one looks perpendicular, right? Great. There we go. So it's perpendicular like so, right? You can see to say this is at least closer to perpendicular, right? Okay, so it's perpendicular to AC. There we go. And we are calling this as F perpendicular to AC. Okay, if I written it properly, let me write it again. F perpendicular to AC. All right, there we go. So these are the two forces that we want to find, the components that are coming from F. All right. Okay, and we know that the resultant itself, F, okay, we can use Pythagoras, will be equal to square root of F parallel, right? F parallel squared, this magnitude, plus F perpendicular, right? You agree? Or if you don't want this, you can also say F itself, F, the first vector F, is also equal to, this is another way of expressing it, is also equal to the parallel force vector, parallel to AC, plus the perpendicular vector to AC. Okay, so either you can use the Pythagoras, or you can use the vector formulation, additional vectors to relate the three components if you are using Pythagoras, or to relate three vectors. Okay, if you're using additional vectors. All right, so we are going to maintain the reference is 0. Okay, so the reference will maintain in this particular case. I will not change it like I've done in the previous other problems, because I always want to just get whichever reference for me is suitable. So the reference is going to remain or 0. Okay, this point here. So having said that, then let's quickly find the coordinates for the rest of the points, and these are A, C, and D. We need these points because these coordinates A and C will allow us to formulate the position vector, and so is D. Okay, and once we have the position vectors, then we can use the position vector to calculate the unit vectors in those respective directions, and later on convert the force, okay, from B to D into Cartesian vector form. And with a position vector along AC, we can do the dot product so that we find so that we find the component that is along AC, the component that is along AC. Okay, so let's start the work quickly. So components for A are going to be equal to A is 0, 0, 4. All right. Components for C, X, Y, Z. Components for C is minus 3, 4, 0. And then D, we have X, Y, Z. This, we are going to have the following information: 4, 6, 0, right? So let's rewrite or write the vector, the position vectors. We have RA, okay, because our reference is 0. So it's either R or A, which is just RA because we have the reference 0 there. So we've taken that, not taking the trouble to say R or A, just RA, it's fine, okay? Because we're coming from a code, our reference is already 0, 0, which is already in the problem. So RA, therefore, is going to be equal to, just 4K, okay? Is that fine? RC, okay, is going to be equal to minus 3I, okay, plus 4J. And then RD is going to be equal to 4I plus 6J. Are we there? So now we need to find, okay, let me just shorten this arrow here so that it doesn't too much of my space. I shorten it a little bit. Okay, I shorten it like so, and then I move this there like so. Great stuff. All right, so now we have the position vectors RA, RC, and RD. Now let's find the position vector RAC. Okay, the position vector RAC is going to be equal to RC minus RA, right? Is that fine? This therefore is going to be equal to minus 3I plus 4J, and then minus RA, we said is just a 4K. Okay, therefore this gives us, okay, it's like I can write it there in front, there's some space. This gives us, if we do the subtraction, this gives us a minus 3I plus 4J, okay, minus 4K. So that is the position vector for RAC. All right. So what else do we need to do? We can now find the unit vector along RAC, along AC, which we are going to do. But for now, let's first find the coordinate for B. Okay, let's find the coordinate for B. So and then later on write the position vector. Okay, so we just go direct into writing the position vector. So we've been told that the point B is located midspan of the road, so it's in between coordinates A and coordinates C. Okay, so remember the rule: when coordinates are within a given line, given two outer coordinates, if it's at midspan, you can add the coordinates and then divide them by 2, x plus x, okay, divided by 2, and so on and so forth, right, in that manner. So let me write directly the position vector for B. Okay, so given, let's say, Okay, you are going to see this explanation that I have here. So this is how you find the coordinates for. So for in this particular case for B, finding coordinates for B. Okay, let me just write here maybe for the sake of everyone. Coordinates for B, okay, which is x, comma, y, comma, z. This is going to be equal to. This is going to be equal to. It's going to be equal to coordinates for B itself will be equal to A. Okay, so given that A here is equal to RA, which we already have. We overwritten RA. Where is RA? It is this one here. Okay, so we are going to have something like this. We'll say AX, a component of AX, okay, plus the component of CX divided by 2. Is that fine? That's X component of B, comma, a component of AY plus the component of CY divided by 2, comma, a component of AZ plus component of CZ divided by 2. So this is what we are supposed to do, right? Therefore, B, X, comma, Y, comma, Z is going to be equal to B. What do we have? AX and AY, okay, at A is 0, okay. So here, we only have CX, okay. What is CX? CX is a minus 3, so we'll have minus 3 divided by 2, because this component 0, okay, I'll write everything 0 minus 3, because CX is minus 3 divided by 2. Okay, I write like so, plus minus 3 divided by 2, comma, AY is 0 also. CY, what is CY? CY is 4, so it will be plus 4 divided by 2, comma, what is AZ? AZ is 4, it is there, AZ is 4, okay, plus what is CZ? CZ is 0, so divided by 2. So these are the coordinates, okay. So from these coordinates we are able to rewrite now the position vector. So RB therefore, okay, RB therefore is going to be equal to, RB is going to be equal to 2 into negative 3 divided by 2 is minus 1.5 I, right? And then plus we have 4 divided by 2, okay, it's a 2J, and then plus 4 divided by 2 also, it is a 2K. So this is therefore now the position vector for B. Okay, is that fine? Thank you. So we have the position vector for B. So now we can find the position vector for RBD. Okay, so the position vector for RBD is going to be equal to RD, okay, minus RB. Is that fine? Sure. So this is going to be equal to what is the position vector for RD? We wrote it down. It is a minus, it is just 4. It is 4I plus 6J. Okay. And then what is position vector for RB? We wrote it down also somewhere. RB, there it is, just on top, is minus 1.5 I plus 2J plus 2K. Okay, therefore my RBD is going to be equal to, my RDB, when we do the subtraction, it is going to be equal to a 5.5 I, Okay, a 5.5i plus a 4j, right? Okay, and then minus, we have a minus a 2k. So we found RDB. Okay, we have found RDB, position vector RBD rather. Position vector, we found position vector RBD. So it's like we have all the position vectors now. Let's see. Find the unit vectors along AC and along BD. Okay, is that fine? Sure. Let me wrap that so that I have some space. I can also wrap this. I think so. Okay, so let's do that. So RBD. Okay, maybe I just copy it and then I move this part something like so. All right, so now let's find the unit vector quickly. So the unit vector BD is going to be equal to RBD divided by the magnitude of RBD. This is therefore going to be equal to 5.5i plus 4j minus 2k, and divided by the square root, which is the magnitude of RBD, 5.5 squared plus 4 squared plus a minus 2 squared. Alright, and therefore this gives us a 5.5i. It gives us a 5.5i plus 4j minus 2k divided by root of what? Root of 50.25. Okay. All right. We found the unit vector UBD. With the unit vector UBD, we can now convert the force of 600 newtons into a Cartesian vector form or into a vector force. So to do so, we have the following expression. The force vector BD is equal to the force magnitude times the unit vector BD, right? And this is going to be equal to 600 times the unit vector, okay? The unit vector BD, which is this one. All right. So therefore, when we do the calculation, we find that our force vector is going to be equal to 465.53i, okay, plus 338, right, 0.57j, and then minus 169.28k. All right, so that is what we find. So with that information, let's now go to AC. We find the unit vector along AC. All right, so we already found what RAC is. We said RAC, okay, RAC is equal to, it is equal to minus 3i, okay, minus 3i plus 4j minus 4k, like so. All right, so let me get rid of this information here, right? I get rid of this information, I think, and this one, and then I think everything. I need some space. All right, so let's now find the unit vector UAC. Unit vector UAC is going to be equal to position vector AC divided by its magnitude, which is magnitude of RAC. This therefore is going to be equal to 3i plus 4j minus 4k divided by square root of minus 3 squared plus 4 squared plus minus 4 squared. This therefore gives us a minus 3i plus 4j minus 4k divided by root of 41. Okay, so we have the two sets of information that we wanted. We have converted the 600 magnitude of force into a force vector. We've also found the unit vector along AC. It is now time to do the dot product so that we find the component of F that acts along the road AC. And from that information, we'll be able to calculate the perpendicular component. Okay, so this is the expression. So we do the dot product. We are going to say force BD, force vector BD dot unit vector AC, right? Unit vector AC, this is going to be equal to, all right, this is going to be equal to, let me see if I can copy this, so that I bring it here quickly, like so. Okay. Like so, dot the unit vector AC. Okay, can I copy it also? I think so, I can. Something like so. Oh, great stuff. It can't fit there, so I'll just put it somewhere there. All right. So we are dotting the two. We are dotting the two. All right. So we are going to have the following expression: FBD, okay, dot UAC. If we do the dotting, okay, I'll write everything else here. So we have a 465.53 times a minus 3 divided by root of 41, and then times I dot I plus a 338.57, okay, times 4 divided by root of 41 times j dot, in that manner, j in brackets. Then finally plus what do we have, a minus 169.28 in brackets times a minus 4 divided by root 41, and then finally times k dot k, like so. So we have this particular expression. So now let's do the dotting quickly so that we find the result. Okay, let's do the dotting so we find the result. Let me rub this stuff on top, okay, because it's now of no use, and you find it in the previous sessions. Moreover, therefore, our FBD, vector force FBD dot unit vector AC, after doing the dot product and you've done the computation, figured using your calculator, you find that, and done the summation, algebraic summation, you find that you are going to have the following result: 99.14, which is in newtons. Right, so that is what we find, and this is the force component along AC. Therefore, our force component along AC is equal to 99.14 newtons. You can convert this, if you wanted to, into Cartesian vector form if the question wanted you to do that, which I was doing the previous questions. But if you just want the component, you can leave it the way it is. You can use Pythagoras theorem, okay, to find the other one, or you can use vector addition. But if you use vector addition, then you'll have to convert this parallel force into a vector, and then do the algebraic sum or the vector addition with the resultant, and then you'll be able to find the perpendicular force. But we don't need to do that now. I guess we do not have time. We can do the Pythagoras, right? So finding the perpendicular, component, we'll just use the Pythagoras, which is perpendicular vector, perpendicular component, okay, perpendicular to AC is going to be equal to, okay, perpendicular to AC is going to be equal to square root, okay, is equal to square root of f, all right, square root of f itself, or fbd, okay, f, okay, squared minus f parallel to AC, okay. Is that fine? So this is going to be equal to, we are going to have the following. What is f? It is 600 minus 99.14 squared. And when you do the calculation, you find that 600 minus 99.14 squared, you find the following: a 591.75 newtons. Is that okay? It is. So let's write down the summary. So the summary of the solution is as follows. The summary of the solution is as follows. Okay. So what we have the parallel force, parallel to AC, yes, is equal to 99.14 newtons. And the perpendicular to AC is equal to 591.75 newtons. Are we there? Okay, I guess we are done. All right. Thank you. Please keep on supporting me. Like my videos, comment, and you can even join the pecs, those pecs that I did open, okay, on the YouTube, where you can support me financially so that I continue producing content for you. Thank you, and see you in my next screencast.